So now I give the floor to Sylvie.
Yes, many thanks. So, good morning. Do you see my screen now?
Yes, we can. Perfect.
Okay, so we can begin. So welcome to the first workshop of HEATERNAL project. I'm Sylvie Douat from CEA, Commissariat à l'énergie atomique et aux énergies alternatives in France. And I'm the coordinator of this HEATERNAL project. HEATERNAL, what does it mean? Innovative high temperature thermal storage for industrial applications. This project is funded by the European Union under Horizon Europe program. So I would like to begin by saying a few words about the general context of this project. As you know, we have to face climate change and environmental impacts due to human activities. We have to face also to geopolitical events and rising energy costs. So let me give you some data. Industry in Europe released 351 million tons of greenhouse gas during the year 2020, and the energy used for direct heating is mainly covered by natural gas up to 50%. Consequently, the European Union has fixed some objectives to be achieved by the year 2030, such as reducing gas emissions by 55% compared to the 19th, increasing renewable energy up to 45%, and increasing energy efficiency up to 13%. So in this quite difficult context, HEATERNAL develops a thermal energy storage to meet industry needs of high temperature heat. And globally, this storage will be able to satisfy the need for decoupling the heat generation from the heat use in industrial processes, and this storage will be able to generate heat during off-peak times and so provide some flexibility in energy demand. So specifically, through HEATERNAL project, we expect to develop a short-term thermal storage up to 48 hours, to develop some new materials for its storage dedicated to medium and high temperature processes. And we expect to enhance the awareness of the challenges and benefits of its storage in industry. After this brief introduction, we propose 4 presentations today. I will be pleased to begin with a general description of the project. Then the second presentation about phase change materials will be given by Ángel Serrano from CIC Energiegund. The third one will be given by Sergei Bafalui from LATET, and will be about 3D models developed for HEATERNAL solution. And the fourth and last presentation will be by Wim Bain from Ghent University, and this presentation will be devoted to thermomechanical modeling of the storage. These 4 presentations will be followed by a questions and answers session during around 10 minutes. So as coordinator of the project, I would like to thank the speakers, Ángel, Sergei, and Wim, for their contribution to this first workshop. So before we start the presentations, I would like to remind you of a few practical details. Note that this online workshop will be recorded, as Hannah already said, and choose the speaker view on the top right hand corner of the Zoom screen for a best workshop experience. You can keep your camera on during the panel session, but please keep your microphone off. And the question and answer session will be based on the questions written directly in the chat during the presentation. The moderator will read the questions, and we will organize the answers. So that's it for the details. Now, enjoy this workshop. Now I will begin with the general presentation of the project, the concept, the partners, the action, and of course its objectives. As already mentioned, HEATERNAL project is funded by the European Commission, which is represented by CNE agency. So HEATERNAL project started in May 2020 and will last 3.5 years. The project aims at upgrading the HEATERNAL technology from level 2 to level 5, thus validating the concept through experimental tests in representative operational conditions. The project brings together 11 partners based in Europe, mainly in Spain, Portugal, France, and Belgium. And 4 partners are public research teams who are focused on prototyping, thermal modeling, phase change materials, and 3D printing. The project also involves 4 manufacturers, 2 from the metal industry and 2 from the ceramic sector, and also an equipment manufacturer, a society specialized in life cycle analysis and technical, economical analysis, and lastly, a society experienced in dissemination and communication. We know that in many cases, industrial processes require continuous high temperature heat and release some millions of tons of carbon dioxide into the atmosphere. Unfortunately, no viable solution exists today for decarbonization of these processes. Therefore, a short-term thermal energy storage will be an efficient solution since it would enable to replace fossil fuels by industrial waste heat or renewable electricity. So the aim of HEATERNAL project is to develop an innovative thermal energy storage to meet the needs of industry using these high temperature processes. The HEATERNAL concept is based on hybrid storage using ceramic and phase change materials, so-called PCM. And this hybrid unit is represented on the top picture of this slide. The lower picture shows that the storage would be able to operate in 3 temperature zones, depending, in fact, on the industrial application. And each PCM in each zone undergoes phase change at a different temperature. And thanks to this transition phase, I would say, each PCM enables to increase the energy density of the whole thermal storage. So you see that the PCM in HEATERNAL concept will decrease the cost and also the carbon footprint of the industries. So considering the integration of internal project, internal solution in industrial processes, 3 use cases are being evaluated. The first one concerns the aluminium industry, represented by Alcoa company. Renewable energy will be stored as high temperature heat during peak production of low-cost and intermittent renewable energy. Then the stored energy will power a continuously operating electric calciner. The second use case is the ceramic industry, represented by Torresid company. For this case, industrial waste heat from a continuous process will be stored and reused in a batch process, such as a ceramic pigment furnace, and the stored heat will be used to preheat air between 650 degrees and 900 degrees. And lastly, the third use case is steel industry, represented by GTEC company. For this case, industrial waste heat will be stored to heat a steel furnace during natural gas shortages or cutoff, and this storage will also be used to maintain the furnace temperature during the weekend when the process is not running. So in all these cases, internal storage will enable to reduce the use of natural gas and in fact to reduce dioxide carbon emission. So in order to perform the project, the activities are being divided into 8 work packages, 6 of which are technical packages, I would say. Briefly, work package 3 is devoted to materials development. Work package 4 focuses on thermomechanical design of the thermal energy system unit. And work package 5 aims at building and testing prototypes. Work package 6 will study the scalability and the integration of eternal thermal storage in industry. And work package 7 will deal with technico-economic, environmental, and social issues, and also exploitation plan. Along the project, we have several short-term objectives. Build and test a 50 kWh prototype in order to validate the eternal concept, maximize the thermal performances of the thermal energy storage unit, simulate the full integration of eternal storage into industrial processes in order to ensure rapid implementation and thus encourage stakeholders to invest in further developments. And lastly, ensure the economic viability and environmental sustainability of the thermal energy system. As a matter of course, the long-term objective of this project is to reduce the carbon emissions from high-temperature industry by 40% by the year 2040, while reducing their dependence on fossil fuels, mainly natural gas. So this brings us to the end of our general presentation. May I suggest you to visit our website, www.heaternal.eu. Now, I give the floor to our second speaker, Angel Serrano.
Okay, I'm trying to share the screen. Wait a second. Okay, can you see now the presentation?
Yes.
Yes. Okay, thank you, Sylvie. Well, my name is Angel Serrano. I am a researcher at CIC Energy Pune, and in this project, I am leading the work package related to the storing material development. Sylvie has already given you an overview of the project, and I will now focus on the phase chain materials that we are developing. The goal is to share with you the challenges that we are facing in this project and the strategies we are following to overcome them. To give you a clear picture, I will start by briefly explaining the overall approach taken in this thermal energy storage system. I will show you the key challenges we are addressing, the design strategy, and the current state of development, focusing on PCMs. And let's start by exploring the concept of the test system. There are 4 main objectives we are aiming for. Beyond the goal of a high thermal storage density, there are other equally important targets, including the sustainability and circularity of the system, as well as its long lifespan. With these objectives in mind, we propose a cascade thermal storage system. The core of this solution is a refractory material containing one or more metallic PCMs. A PCM is a substance that changes from solid to liquid or vice versa at a specific temperature, storing or releasing energy as latent heat. This makes them very attractive for storing energy, especially in narrow temperature ranges. When we need to store energy over a wider range of temperature, using different PCMs with different melting points at various levels help us to maximize the heat that we can store by taking full advantage of the tank's temperature profile. This cascade system is not new. They have been proposed before in the literature, mostly using molten salts. However, our innovative approach focuses on very high temperatures, So we are developing 3 levels of metal-based PCMs working at temperature from 550 Celsius degrees to 700, between 700 to 800 degrees, and up to 900 degrees. There are also significant innovations on the supporting material side, which I won't discuss here. But briefly, we are working with 2 main approaches. One uses standard manufacturing processes. This facilitates the scaling of the solution with existing industrial processes. And the second approach involves more complex geometries using additive manufacturing, which give us more freedom to optimize the heat transfer and maximize the PCM content in the system. And now that we understand the approach, what are the main challenges from the PCM perspective? First, we face challenges related to achieving the specific thermal properties that are required, such as melting point and energy density, all these while keeping a low cost. We also have challenges in ensuring that the system can be recycled, as well as minimizing the energy consumption and carbon dioxide emission during its production. But I would like to particularly highlight the challenges related to the lifetime of the system. First, the reliability of the PCM during thermal cycling. The PCM must maintain the initial thermal properties over many thermal cycles. It must also be compatible with the heat transfer fluids, which in this case is air. This makes oxidation processes critical since we are working with metals. And finally, the PCM must also be compatible with the refractory materials, both chemically and in terms of thermal stresses derived from the different thermal expansions of both materials. We are addressing all these challenges on several fronts, starting with the selection of raw materials and PCM design, incorporating also inputs from the life cycle analysis, and working in parallel on the formulation and design of the refractory materials. We also use thermomechanical simulations to help to define the most suitable geometry that mitigates the mechanical stresses. Let me now give you a brief overview of the steps that we follow to design the PCM, in this case in close collaboration between CIC Energigune and CEA. The first step was to select the raw materials, the raw metals that could form potential alloy candidates. For this, we apply criteria related to energy, stability, and cost, focusing on metals with low vapor pressure and excluding those with high cost in terms of euros per kilowatt hour. This allowed us to select some metals that we can use either as pure metals or in binary and ternary alloys. With this range of metals identified, the first step was to review the literature for existing options. And while some meet our basic requirements, there are temperature ranges where suitable options are scarce or even unavailable. In these cases where we need a specific melting point, but there are not available reported options, we use the CALFAT methodology. With the CALFAT allows to calculate the phase diagrams of these alloys and thermodynamically predict which composition could be of interest. We focus on those with invariant transformation within the desired temperature range and with expected high transformation enthalpies. By combining both the literature research and CALFAT methodology, we were able to identify a series of candidates that can cover the 3 targeted temperature ranges. Once we have the candidate formulations, the next step is to bring these materials to life and to test their potential. We start by optimizing the synthesis protocols for the alloy, focusing on processes that not only give us better properties in the final material, but also are more cost-effective and easily scalable. All this process is followed by a deep characterization of the material. This characterization not only confirms whether we have achieved the expected alloy, but it also allows us to obtain the key thermophysical properties that fit the thermomechanical models. The characterization includes microstructural and compositional analysis of the alloy, as well as measurement of the coefficient of thermal expansion, latent heat, specific heat, thermal conductivity, diffusivity, and more. Once the ideal properties of this alloy are confirmed, we move on to a critical test, the thermal cycling of the around the phase change temperature of the PCM. And I say that this is a key test because it evaluates the evolution of the thermal properties over 100 thermal cycles in the presence of air. From all this work, well, what we obtain is a portfolio of different PCMs with different advantages, like high energy density, low coefficient of thermal expansion, low cost, or even low density in terms of mass per volume, which allow us to design systems very light. And to conclude, the next step will focus on ensuring the compatibility of these PCMs with the refractory materials, specifically aiming to identify any degradation mechanisms if any issue is detected. On the other hand, we will work on the integration of the PCM into the refractory, which, while it can be simple for more standard geometries, might present a challenge in the case of complex geometries produced via additive manufacturing. And finally, the selection of the best PCM will be based not only on their thermal properties and stability, but also on the life cycle analysis and thermomechanical aspects that could compromise the mechanical stability of the system. Thank you all very much for your attention, and I will be willing to answer your question at the end of the session.
Thank you so much, Angel. Just want to quick remind you that you can write your questions on the chat, and we will read all your questions at the end of the presentations. And now I give the floor to Sergio.
Hi, good morning, everyone. I guess you can see my screen already.
Yes, now it's on.
Okay. Thank you. Yeah, so hi everyone. I'm Sergi Bafalui. I'm a researcher in LEITAT, and I will be speaking today about the 3D printing test geometries that was already slightly introduced by Angel and Sylvie previously. And to get into the topic, I will begin first by explaining why additive manufacturing for the thermal energy storage units. We'll continue with a description, detailed description of the whole additive manufacturing process. And finally, I will summarize the developments that have been carried out so far in HEATERNAL project. Okay, finishing with quick next steps slide. So to begin, why additive manufacturing for the thermal energy storage units? There are several reasons for that. Compared to the conventional manufacturing technology, it is quite disruptive in terms of, for example, design freedom. I think it's widely known already that 3D printing can lead to geometries that are not easy to fabricate through any other conventional method. And in the case of dealing with thermal energy storage, this can lead to a lot of advantages. Amongst them, there's the fact that you can print high surface area geometries, such as this TPMS, which stands for triple periodic minimal surface. And as you can see in the images, these sort of geometries bring a significant increase on surface area of the material, right? And thus on the surface area by volume ratio. This means in the end that the thermal management is quite more efficient than expected, and then a heat transfer coefficient improvement is expected by 30 to 80%. In addition to this design freedom, there's also the capability to customize a part. And as you saw earlier, Sylvie was explaining about 3 different cases that we are dealing with in industry. However, you can imagine that each case on each company will be different, and additive manufacturing allows for these differences to be addressed in the optimal way by bringing customized solutions to each necessity. Okay. Additionally, in addition to that, there's also sustainability aspects and the capability to perform system validation at small scale, which is not easily done by conventional manufacturing technologies. So to continue, I will briefly describe the whole manufacturing process. It does not begin with 3D printing itself, but it begins with the formulation of a mixture. This formulation occurs by basically, well, I have earlier than that, I have to say that the technology that we are using in HEATERNAL for the 3D printing is fused filament fabrication, okay, which means that we will need a filament, right? So to formulate a filament, we will need a polymeric matrix, we will need the ceramic compound that will basically conform the geometry of the printed part, and then we will need some additive to increase the plastic behavior, the flexibility of the material, and so on, right? The first process is to perform the mixture of these components and extrude them into a continuous line, right? This extrusion then ends up with the pelletizing of the filament, this first filament, which is then used to extrude it again in a filament extruder, which means that the final diameter will be calibrated to fit any 3D printing equipment, and spooled for being able to handle it, right? Next, as it's shown in the picture, there's the fused filament fabrication process, in which the filament comes through a heated nozzle to deposit the material layer by layer. And finally, there's the binding and sintering process. This process is a challenge, especially because of the fact that we are removing the polymer first and then densifying the part to achieve the high densities needed for the better test unit performance. Okay. The challenge within this also lies within the fact that during sintering there's a shrinkage on the part that will surely distort the final geometry from what was the nominal dimension. So to continue, we'll begin with some of the developments that we've been carrying out. First, there's the very same TPMS design selection. There are many TPMS design geometries, and in the case of HEATERNAL, we have made the decision of the geometry, and not only the geometry, but also the percentage of each component within the geometry based on the system requirements that include the pressure drop, so minimizing the pressure drop, increasing at a maximum the heat transfer. These two are generally a trade-off. So generally, if you try to reduce the pressure drop, the heat transfer will be also reduced, and so on. And then there's, as I was saying, a trade-off between these two factors, and also the system requirements based on the system dimensions themselves. So the 3D printer, the dimensions needed for the industrial cases, and so on. Okay. On the other hand, there's also the materials and process limitations, which, for example, include limitations regarding the 3D printing minimal printable size, includes the maximum dimensions of the 3D printer, and includes as well the mechanical stability required by the material for it to be processed into the sintering stage and mixed with the metal or the PCM afterwards. Okay. In the current case, we have led to this solution, which involves a 23% air volume, 27 refractory, and a 50% PCM. You can see on the right images that those different phases, however, they are distributed in a 3D volume. On the other hand, regarding the advances in the material formulation itself, the material formulation, it's also quite challenging because of different aspects needed to be taken into account when performing such formulation. Okay, amongst them, there's the material flexibility that you need for the very same spooling process after the filament extrusion. The material rheology has to be perfect for the filament to be possible to to have an optimal extrusion. Then the thermal properties need to fall into the suitable temperatures for fused filament fabrication. And finally, also the ceramic percentage needs to be as big, as high as possible in order to ensure the maximum density is achieved after the sintering process. However, as it is noted here, this last consideration is a little bit contradictory with the first one, in which we look for material flexibility. So as we increase the ceramic percentage, for sure, the material flexibility will decrease. And this is tried to be overcome by the use of several additives in the formulation. As you can see then, the material formulation takes into account all those previous steps that I was just explaining in the last slide, which makes it even more challenging, okay? You can see that we have performed already material flexibility studies that to ensure the material can be pulled up and no breakage occurs. And we have also been including the binding studies in order to take into account the very last stage of the process to ensure that it is taken into account since the beginning, and we do not find surprises to that regard at the end of the project, right? Finally, to continue, we have already started with filament fabrication itself. We have found a formulation that that has around a 60% ceramic on it, which is quite interesting already. We have managed to extrude a filament. Sorry, I'm sharing this video as well, in which you will see the filament being spooled, meaning, well, you can see the high flexibility that we have been able to obtain. Yeah, and it may look simple, but as you saw on the last slide, we have tested up to 20 almost formulations with different polymer percentages, different ceramic percentage, and a variety of additives. Also, we have already used a lower ceramic percentage formulation to print a first demonstrator, as you see in the last picture of the slide. Here at the bottom, you can see the stability of the filament diameter as it is formed, which is an indicative. Generally, a filament for 3D printing should be 1.75 millimeter thick or 2.85. In this case, you see that we are dealing with 1.75 millimeter, and you can see that the diameter is stable enough for it to be processed. So to finish my presentation, the next steps would be to fabricate the test specimens with this 60% ceramic material, continuing by the binding and sintering studies on printed parts already and not on filament as we have done so far. Then also consider the design of an enclosed geometry to perform further testing in Sieg-Energiegune premises. Then also Sieg-Energiegune and Angel would integrate this PCM into the matrix that we are generating, and they would also characterize and validate the final part properties with aeration test, amongst others. Okay, I think that's all, and thank you for your attention, and we'll be looking forward for your questions at the end of the talk.
Thank you so much, Sergi. Now we can move to the last presentations from Vin.
Yes. Good morning, everyone. So I'm Wim Bene from Ghent University. You should be able to see my screen by now, and I'll talk today about we've seen material developments, we've seen some new production methods with 3D printing, and then the next step is how do you take those two elements and make a system out of it? How do you design those things? So it's about the thermal energy storage, system design, and model integration, essentially. And it focuses on the system design. There's two major questions here. There's a thermal problem and a mechanical problem. The thermal problem is the question how to charge and discharge the heat. So there's heats coming from a source. Usually you have a heat transfer fluid like air, a temperature, and a mass flow rate that you can use to heat up your storage system. On the other hand, discharging, you have the same thing. You have a heat transfer fluid flow and you want to discharge as much heat as possible from refractory and PCM to that heat transfer fluid. That's a thermal problem. Second problem is the mechanical one. You have a system which goes through thermal cycles, which rather large temperature differences, because we're doing storage at high temperatures, usually also means high temperature differences. That means a lot of thermal tensions. They also have difference in thermal expansion between PCM and refractory. So you really need to pay attention to mechanical issues so that the system doesn't fail. So let's dive into how we can construct our system. There's two methods we're evaluating. The first one is traditional manufacturing. So we are casting refractory bricks, essentially large slabs in which we put air channels and PCM volumes. We have about 12 tons per brick we can do, about 2.2 meters in diameter, and a height of max a quarter meter. We can stack these bricks up to build actually a storage system. So it's a traditional manufacturing method. We know the constraints of this, and we can already design it. On the other hand, we have the 3D printing. The previous presentation discussed this 3D printing strategy. The outer dimensions you see here are the dimensions which we can maximally print in the systems we have now. But this is, of course, still in the development. But I will show you that it's, from a system design point of view, quite a promising technology. Okay, now we go to traditional manufacturing, and first question you can ask, how can we geometrically define these things? And we've defined actually several possibilities you see here on top. The gray is the ceramics, the refractory, the red is the PCM, and air is the blue air holes, essentially. And you have different types of geometry you can build with this system. And you want to know what's the optimal units to start building. And to know that, we take the three variables on the right-hand side. The bottom two of those are something I think everyone who does heat exchanger design knows. You have heat transfer rate and pressure drop. You want a high heat transfer rate and a low pressure drop, but usually if you increase heat transfer rate, you also increase pressure drop. So there's a trade-off between those two. Important in this case is that the dominant thermal resistance will be your air compared to the thermal resistance of your ceramics and your PCM. Now, besides these two classic variables, you also have stored energy. So how much energy can you store? What's the thermal mass of your system? And that is where our PCMs come into play, where you have the latent heat, which you want to be as high as possible. Secondly, our geometry will define how much volume percentage PCM you can have compared to the refractory and air. If you compare those three variables for one of these systems, you get these type of Pareto fronts. So the optimal points where, for example, your stored energy is, you can't increase your stored energy anymore without increasing pressure drop or decreasing heat transfer rate. And all of these points form a front. If you compare all the fronts for these different geometries, you find that that ring design actually obtains, in the regions we're investigating, the best performance. So we went for those rings. Now then, this is a very crude analysis based on correlations for the heat transfer rate, for example. We go into further detail and sorry, I was a bit ahead. We can first compare this Pareto fronting with the 3D printing. So we have traditional, now the 3D printing. And what we see is that in terms of stored energy, the 3D printing is better. In terms of heat transfer, it's also a lot better. In terms of pressure drop, that's of course a trade-off. Your pressure drop is higher. The main thing we still have here is that we're not sure of all the manufacturing constraints, so the minimal wall thickness. So at this point, we have to wait for those to further the thermal design. But based on what we find at this point, it's very promising. It's a very promising technology. Now, if we go to our traditional manufacturing, you need to make a thermal design model. And then you need to put inputs and outputs to the system. And how does this look like? This looks like this. You have a temperature on one axis, the y-axis, and time on the bottom. And you apply a cycle of charging and discharging where you have an air inlet. And we've defined it constant now for a certain amount of time. And you apply this to a thermal model. And from that thermal model, you get the temperatures of the outgoing air, but also temperature inside your systems of PCMs and refractory. And you want as much energy stored, of course, as possible, and thus as high possible temperature difference between your in and your outgoing air. How do these thermal models look like? Well, we have different levels of complexity, because the more complex you make your model, the longer the calculation time will be. And this is, I think, the more complex one. So it's a CFD model where we're simplified our airflow a bit, but the heat transfer in the ceramic and PCM is simulated in a finite volume method. You can see a quarter of the system modeled with 10 bricks in total. You get temperature fields, and if you look on the right-hand side, you also see that you can track what PCM volumes have molten over time. We make geometric adaptations and check with these models to obtain an optimal solution for a specific problem. This was our thermal problem, so I've shown you how we try to solve these things. The second thing is our mechanical problem, and it's a thermomechanical, so you get thermal fields and dust stresses. Now, what actually happens is you have a refractory brick, you heat it up to about 800 degrees Celsius, and you add to it PCM pellets, which will melt. And at 800 degrees Celsius, it is in somewhat of a stressless state, it's annealed, and the PCM is liquid. But then the system cools down, and it should be able to cool down to 25 degrees, and you get stresses due to differences in temperature field, but also differences in thermal expansion. And besides that cooling down phase, you also get a cycling loading phase. Here it is between 480 and 780 degrees C. So we want to investigate those things. How do we do this? We do a static structural analysis. So we take our temperature fields from the thermal model, implement them in a mechanical one. We use linear elastic material modeling, basically because of the simplicity, and it is a conservative approach to material strength, and we want to be conservative in this regard. And we apply a minimal maximal principal stress criterion to check if our design is good. And what we noticed with the original design with the rings we had, we noticed that both compressive stresses, so the max principal stress, min principal stress, we have two problem zones, which we notice. You see here, an enlarged deformation of a part of a brick. And around the air holes, we have too high compressive strength. In the corner, we have too high tensile strength. So based on that model, we can propose an improvement. We separate PCM rings, and if we do that, we see a decrease in the stresses below our safety level. So we're moving forward with that design. So we have an interaction between thermal modeling and mechanical modeling, of course. So to conclude, there's four major aspects here. You have one, the material properties of your refractory and phase change materials. You have the use case specification. So what's your inlet and outlet, your inlet specifications for charging and discharging. And then you have thermal modeling. You want to optimize heat transfer rate and pressure drop and stored energy. But the mechanical problem, you don't want it to break. And all of these things interact, and you should integrate them in an iterative approach for proper design. So that leaves me to thank you for your attention and hand back to Floor.
Thank you so much for the presentations. We have 3 questions in the chat and one hand raised that I will allow to speak up in a minute. Let's start with the questions. The first question, I think it was addressed to Sergi. It's what kind of technology is available which incorporates metal PCM 3D printers?
Yeah, so for the technologies, I think the very same that we are using could be used as well. There are several 3D printing equipments that allow to print multiple filaments at the same time, so multi-material printing. However, there's the inconvenience of the sintering process in which different shrinkage would probably be occurring between the metal and the ceramic. So I don't think it is the best idea to use that technology. I guess in the future we will see new technologies addressing this multi-material printing opportunities. I think nowadays it is done in some equipments where they mix different alloys, for example, but in general they are materials that are quite similar in terms of thermal properties, so they can be printed similarly and with a nice interface between them. For the case of a metal with a ceramic, I think we will still have to wait a bit more for it to happen within the same process.
Thank you. Now we have two more questions on the chat, and I think it is addressed to Wim. The first one is, do you have oxidation issues in the high temperature metallic PCM, either during operation or during manufacturing of the composite? If so, how do these affect the performance?
I think Angela is better suited to answer this question.
Yes, thank you, Wim. Yes, of course, we have oxidation issues in the metal PCMs. The first solution that I can give is, okay, we can change either the heat transfer fluid instead of air using an inner gas, or we can use a protection layer in the metal alloy. But it is against the concept of this project. We want to keep the cost very low. So rather than trying to avoid the oxidation, we are trying to take advantage of this oxidation. So during the design of the PCM, we are taking into account that we are going to have oxidation, but we are trying to obtain a stable oxide layer in the outer part of the metal alloy. Why this is beneficial? Because it avoids the contact of the air with the inner metal alloy and the extension of this oxidation. We have tested over 100 cycles this behavior under air, and we detect this initial drop of the enthalpy, which means that we are starting to have some oxidation, but this stabilizes over the cycle. So in the best scenario, we have detected just a drop of 1% of the enthalpy, of the initial enthalpy, and in the second or third option that we have, the drop of the enthalpy initially is 15%, but it keeps stable. So yes, we have oxidation, but it is even beneficial in the long term.
Okay, thank you. The next question is why charging and discharging temperatures differ by 200 and 300 OC?
Yeah, I think I can answer that question. It are representative values for one of our use cases. So the 780 degrees C was representative of a furnace, waste heat essentially coming out of the system. And then 480 is preheated air, which you do the final heating with the system. So these temperature differences are quite large, but it is what we found for the use cases. And I think it is something which is specific to the high temperature industries that you have these higher temperature differences. Hope that answers the question.
And the last question that I have is what kind of PCM are used, inorganic or organic?
These are inorganic, they are metals. We are addressing the high temperature, and thanks to the wide variety of metals that we can choose, we can tune, I wouldn't say easily, but we have a lot of options to tune the thermal properties and obtain different melting points, but they are metals.
I don't see any more. Just one. Have you thought about mixing PCMs?
Do I answer? Okay, yes. It is an option, but we want to take advantage of the temperature profile along the tank. Because we have a temperature profile, mixing the PCM in one specific level is going to decrease the amount of heat that we can store. It is more beneficial to use the optimized melting point, imagine in the bottom part of the tank, and use a totally different PCM in the upper part, rather than mixing all of them.
One last question that I just received. Can you comment to the economics of using metal PCM?
Yes. During the design, one of the criteria to select the metals was the cost. And the cost, not only in terms of euros per kilogram, but euros per kilowatt hour. Taking into account that we are using phase change materials and the latent heat is really high, the cost is really high, really low in comparison with sensible heat. The metals we are using are very cheap. One of them is iron, aluminium, and overall is cheap if we take into account the energy density of this phase transition. So the economic is one of our criteria to design and to select the PCM.
I see one last question to Professor Vine. I would like to know the numerical simulation methods and approaches.
Okay, so as I said, there's different levels we're using. Most complex level uses finite volume, with actually at a certain point a CFD resolved air channel. And then we solve energy equations in the refractory and the PCM, so it's a conjugate heat transfer problem. In the phase change material, we didn't solve the flow equations because the thermal conductivity is so high that we don't really see an effect of, we don't see an effect on the overall performance of that natural convection there. But this is a calculation which is very expensive, also because of the time we have to simulate this. This is for hours in total time, so you can imagine how expensive it is. So we reduced it first by simplifying the air channel, not solving the flow equations, but using essentially a calculated heat transfer coefficient from a correlation. And then secondly, we used a first order approach in Modelica, where we link essentially building blocks with a constant resistance and a thermal capacity which varies with PCM. And we use that model in Modelica actually to quickly check design changes and then validate them with more complex approaches. So I hope that answers your question.
And we don't have any more questions. So I think that's it. Thank you so much to all the speakers for the enlightening presentations, and thank you also to all the participants that attended this workshop today. We will make this video available on the website and also on social media, and we will send it, share the link with you. And also, if you want, you can also contact us by going to the website, the project website, and you will find the contacts to the project. So thank you so much once again, and see you soon.